So, good afternoon to one and all present over here.
Slide is visible, sir.
Yes, sir. So today we're going to cover about quantum simulators. We are about to cover 4 modules: Qiskit, Penny, Qzine, and Quniverse. So we make it as simple as much as possible. So in order to understand Qiskit simulator, we need to understand why we go for quantum computation, right? So the first tool is Qiskit. Qiskit stands for Quantum Information Science Toolkit. So I will write over here for your understanding. Qiskit stands for Quantum Information Science Toolkit. So this is the abbreviation, right? So Qiskit is a framework. It is a framework. It is a framework which contains all the libraries, packages. It is not a Python tool. It is a quantum framework. Imagine in this system. Okay. So it is a framework which will support two fundamental purpose. One is for simulation. One is for simulation, and second one is for real execution. So real execution. So what type of simulation you can do? You can do any experiment with the quantum in nature, and you can execute real-time quantum system. Okay. So two ways you can use this tool framework. So in this framework, they are providing multiple languages support. One is Python. The another one is Rust and C native. So C native. Okay. So 99% of time we'll use Python. So that is why Qiskit is famous for. So if you want to create any circuit, you can go by Python. Okay. So this we should be very clear what Qiskit will offer. Qiskit will offer a lot more. Whatever we are discussing with Python, it is a little bit interface. Okay. So technically, Qiskit is open source SDK. So SDK stands for Software Development Kit. So I'm telling all this acronym for non-CSE people. Software Development Development Kit. Okay, which normally consists of IDE. Okay, Integrated Development Environment. So normally they will call integrated development environment. Okay, it is such one kind of SDK, open source. So open source means anybody can download this tool, anybody can modify this tool according to their purpose. So you have 100% of freedom. So that is the main advantage of using open source. Take an example of Windows, MS Windows, Microsoft Windows, which is an operating system which is a proprietary based. Proprietary based means it is not a open source, which is a closed source. Okay, take an example of any Linux. It could be Ubuntu, it could be Fedora, it could be Red Hat. So all these are open source. So open source means you don't need to spend any single rupee for this. You can download free, okay, free of cost. I hope I am wearing proper headphone, proper internet bandwidth. My voice is clear, I think so. Yes, thank you. Fine. So open source means you can download for free, and it is very quality against MS Windows, because 99% of the web server are installed over Linux operating system. Okay, sometimes people will think if something is open, it could not be a quality one, but that is a wrong aspect. When compared to MS Windows and Linux, in my experience, I am using operating system for past 16 years. If you add up to my diploma and UG, up to 20 years I'm using open source. Very rarely it will get hanged, and very rarely I will get a lot of error messages. So most of the time it is very stable. Okay, so that is one good quality about open source. Okay, so open source, take an example of Ubuntu. Ubuntu. So Ubuntu you'll get update 25 times per year. 25 times per year. Okay, so I started in nearly 2000. Sir. I started to work with computer nearly 2000. Okay, while studying my diploma, I started. So I gave a better glance, right? Boss Linux is created by Indian government, but unfortunately, it is not that much get popular. You can use Ubuntu. So if you want to use Ubuntu, any Linux, you can use Ubuntu, which is very close to Windows. You will get a very lightweight user experience. Okay. So this open source SDK using for working with quantum computer. So what IBM did, they integrated this WSKIT framework with the actual quantum computers what they build, and it will help you to use quantum circuit. You can use operators and primitives. So all this stuff you need to know if you want to write a quantum algorithm. So quantum algorithm composes of quantum circuits, operator, and primitives. Okay. So I'll share this slide. Please go through all this link. You can find a GitHub link. You can find GitHub link. It contains the whole source code of QSKIT. The whole source code of QSKIT. So you cannot find source code for Windows. QSKIT GitHub if you are searching. So whatever they developed, you can see each and every individual line of this entire framework. So this is the meaning of actual open source. Okay, you can download this tool. You can modify according to your wish. So go to QuizKit. Whatever they developed in this QuizKit, each and every module for circuit, they written each and every tool, library packages, including Python 5. So this is one example, right? So this is one example from the software. Okay, they gave each and every description, each and every description. So this is the true nature of open source. Especially if you are doing R&D, you need to modify according to research. Okay, only open source will help you. The second part is Qiskit ecosystem. They develop software, not only the software, they build the entire ecosystem. They will give extension, API to interconnect with other tools. So this is one beautiful aspect. Okay. So if you go for open source, you are not holding for yourself, and you need to collaborate with each other tools. So it is like a win-win situation. Okay. So most of the time, the proprietary software, they won't give extension and support for other software. But in case of open source, they need to, they're supposed to give. They're supposed to give. We will cover, sir. We will cover. We'll cover. So go for ecosystem, Qiskit ecosystem. Okay. So you can have so many open source library. So if you are interested, you can create your own library. So this is what I told. Okay. So here you can see what are the source code maintained by IBM, what are the source code maintained by community. Even if you become good at one particular topic, one particular research, you can design some code and you can provide some solution and you can upload in the repository, and IBM will support that repository. Okay. So not only from IBM, even some Google code is there. If they are translated into Qiskit version, they will support. So not only from IBM, so anybody involved in quantum research, they are able to contribute code for this repository. So these are few repositories. So somebody asked what is the other ecosystems, right? So these are the ecosystems. It contains each and everything, right? So algorithm, networking, quantum dynamics, even a game. If you are building using this Qiskit, you can able to upload. Okay, we discussed about QBraid in previous session. Okay, QBraid is also there, and you can add on for each and every module, right? If you want to minimize the larger circuit into smaller one, here they gave Qiskit add-on cutting. So likewise, Unit Explorer, I cannot recommend. Your domain is different. Your problem of interest is different. You start to learning quantum and try to explore all these tools. And if there is no tool available for your problem, create one, then upload. Create one, then upload. If you go to this repository, you will get idea how to create a repository. You need to give your problem statement and you need to tell what are the files involved within your repository and how to use it. So each and every time you need to add a README file, how to use your file to execute that particular problem. Okay, so this is for Amazon. So if you want to use Amazon, you can use Qiskit for that. So not only for IBM Qiskit, it will support each and every tool. Yes, definitely you need to write in Python language, but if you are familiar with native C integrated with Qiskit, you can write in C also. If you are familiar with the Rust, you can write program in Rust and you can integrate with Qiskit. So in future, IBM goal is to develop a frictionless community. So whatever the language you know, you can use that language to create any tool. So this is their ultimate aim. Okay. So I'll share this link with you. You go and explore in your free time. So this is the ecosystem, and this is GitHub repository. Sir, tutorial is available. I will tell the link. I will tell the link. Don't worry about that tutorial. So let me finish this slide. Obviously, we will cover all those topics. Whatever you have doubt, we will cover. Okay. So the next thing you need to install Qiskit in your Jupyter notebook or Google Colab. You can use these two commands. So these two commands will require for visualization to install IBM runtime. Suppose if you want to run your IBM hardware, you need to use the second package. Okay. So this is how you need to do programming in Qiskit. So Qiskit stands for Quantum Information Science Kit. So it is a open source framework for quantum computing. Rightly, I said it is not a language. Okay, it is a framework. So framework means it will give opportunity for each and every tool within itself. Okay, it will incorporate more and more language into it. It will support more and more language. Okay, it provides tool for creating and manipulating quantum program and running them on prototype quantum devices on IBM quantum experiences over cloud-based access. So whatever you write, whatever you create a circuit will be able to generate in this form of code, and you can able to run in multiple platform. You can run in Jupyter Notebook or Google Colab or QBraid or any Python notebook you have. You can run it and be able to see output in different ways. Okay, this is from IBM Composer. So this is from your Jupyter Notebook. So multiple ways you can design a code, design the circuit. You can write code for it. Then you can see output out of it. Everything is based upon cloud-based access, or you can install in your standalone laptop. Okay, so that is the beauty of this tool. So we will see how your Qiskit is get executed. So suppose if you are working with your laptop, I share the laser pointer. Suppose if you are working with your laptop or your CPU, you can design some circuit. Okay, your classical computer, you are using classical computer to program to design some circuit, and this will go to cloud control. Okay, so whatever you are doing, you are submitting your job through cloud. Okay, the cloud will take all your inputs and it will go to the data center. That quantum data center will convert all your classical program into quantum signals. Okay, it will convert into quantum signals. So all these quantum signal in the form of microwave pulses. So these microwave pulses will come down. So here it will reach your quantum processor. Okay, your quantum processor will do all the computation. Okay, after doing all the computation, it will send back result in the form of microwave pulses. So these microwave pulses again translated into your actual output. So this quantum output is converted into classical output in the binary form. Then you will get your result through your laptop or CPU. So this is how it will get executed, right? So I gave a small architecture of quantum computer in the left and right hand side. You can see, right? So here I mentioned memory. Memory means does not hold for longer time, only for milliseconds, even nanoseconds it will hold. Okay. So there are four important steps involved in Qiskit workflow. One for building. The first one is build. So in build phase, what you're supposed to do, you need to design and develop quantum circuit. So once you design and develop quantum circuit, then you need to transpile. So transpile is equivalent to what you can say in classical compile. Okay. So if you have a program, you can use compiler to convert into that machine architecture. In the same way, if you are writing any code in quantum, okay, in Qiskit, in Python, let's say in Qiskit, you are using 5-qubit system. You are using 5-qubit circuit, but actually, if it is running over 127 qubit, okay, your program is converted according to the 127 qubit. So here, what happens? It will optimize your circuit efficiently to run on your hardware. So user don't know how to transpile. Okay, the transpiler will take. So transpiler, it is like conversion between your actual quantum code into quantum hardware. Okay, suppose if you are doing simulation, you cannot go for transpile. You just you can execute right over there. So to do real execution, you need to go for transpile. Okay. So next, what you are doing, you are validating and evaluating your quantum circuit. Okay. After transpilation, you need to verify whether the circuit is valid, contains any syntax error or any kind of mismatch between the system architecture and program circuit construction. Then it will evaluate. So if it is good, if it is not going to do any harm for your quantum system, it will allow, it will execute. Okay. So transpilation, after transpilation, verification will happen at Qiskit backend. You no need to bother. So they will check your code automatically by the software. If the circuit is valid, then it will allow for execution. Okay. So real quantum execution will go under Qiskit runtime. Otherwise, you can do all your simulation using simulator. Okay. So you need to remember two cases you are able to execute your code. One is simulation. One is simulation. Second one is real quantum execution. Real quantum system. You can say computer. Real quantum computer execution. Here I will mention quantum computer. Sometimes it will confuse. Okay. So simulation, you can simulate in your local laptop. You can simulate in your local laptop or CPU. So this is possible. So 95% of the time, when you are learning about quantum, no need to go for real quantum system. Okay, whatever you have your laptop configuration, you can execute in your laptop. You can do all simulation. So once you got familiar, once you require, you definitely need to execute on real quantum system, then go for the second type. Okay, so majority of the time you no need real quantum system. No need real quantum system. So we'll discuss one by one step. In the build phase, you can create a quantum program that represents the problem you are solving. So this will happen by creating a quantum circuit. Okay, so building a circuit with QT, which lays the foundation for dual OS is also good, but more and more if you are using Linux, it is easy for you to catch up all in-depth point. To catch up all in-depth point. Okay, the foundation of quantum programs are quantum circuits. Okay, so once you design quantum circuit, you know how to write a quantum program. Okay, then what you're supposed to do, you need to do so many operations. You need to include gates, then you need to do measurements, then you need to reset whenever if you want. Okay, so this is an example for quantum circuit. This is an example for quantum circuit. Okay, to build quantum circuit, you need to initialize a register. Okay, number of qubits. This Q0, Q1 are belongs to qubits. Okay, if you want to add any additional qubit, you can add. And this part belongs to classical bit. This part belongs to classical bit. Okay, so whatever the information you have, those quantum information is backup to the classical bit. Classical bit. Okay, all your quantum information converted into classical. So you can say like this: all your quantum information converted into classical bits. Okay, so what it means when you do measurement, so this is the measurement purpose, measurement operation. When you do measurement, all your quantum information is converted into classical bits. Okay, so this is an example Python code. This is the example Python code equivalent for this circuit. So when you design a circuit, it will generate code in this way. When you design a circuit, you can get code in this way. Okay, so each and every output of quantum circuit is encapsulated by primitives. So primitives you can consider like a data type. Okay, primary data type. Okay, so you have two types of primitives. One is sampler primitive, one is estimator primitive. So sampler primitive, no need to say Python. Uh, um, I will tell, sir. I will tell. Wait for some time. Okay. So output of sampler primitive is quasi probability distribution over all possible outcomes. Okay. So circuit should include measurements. Okay. So sampler means you are executing on a real quantum system. Suppose if you are doing only simulation, then you can go for estimator. So estimator output is the expectation value of an observable. Example, cost function of an optimization function problem. Okay, you no need to go for the final solution, just you want to know the intermediate step. According to the simulation, you are able to get the expectation value. So circuit should not include measurements. So note down these 2 points. So this is for real execution, this is for only simulation. Okay, so if you make measurement, then this will turn into sampler. Okay, so Qiskit includes a library of standard gates and common circuits. Okay, we will see one by one. One is standard gates. So standard gates contains Hadamard gate, Pauli rotation gates, CNOT gate, and quantum Fourier transform. You can do n number of gates, and you can use variational answers. So this is something different. Okay, suppose if you want to do quantum annealing, you can go for variational algorithm. You can change your parameter. especially if you are working for quantum chemistry, or if you are working for combinations, permutation, including so much of mathematical difficulty, you can go for yes, IPNB. You can go for ansatz. Suppose if you want to compare your quantum circuit, your algorithm with other algorithm, then you can go for benchmarking. So how good your circuit is while comparing with your quantum value. Okay. So note down this term called quantum volume. So quantum volume is a new key or new benchmark, or you can say quality. Okay. Quantum quality determined by IBM. Okay. So IBM define this quantum volume, and you can able to calculate the quantum volume of your circuit. By doing so, you are able to do benchmark over different devices, different circuit. As we discussed in previous slide, uh, I won't cover a D wave. Please watch this. In transpile phase, you rewrite your circuit in the form of that can be efficiently executed on your quantum device. Okay. So whatever the program you are written for number of qubits, it will be exactly mapped to quantum hardware available for you. Okay. Even if you are writing for 10 qubit, if the available system is 127, your code is transpiled to 127 version. Okay. So this is the advantage of transpile. By doing so, you can efficiently execute on real system. Okay. So as we discussed, each and every quantum computer provided by IBM are subject to constraint. So each and every architecture is different. The way it will get executed also get different. Okay. So basic set, only a limited set of gates are available directly executed on the hardware. Other gates must be rewritten in the terms of these basic gates. Okay. So some quantum computer will not support some basic circuit. So you need to convert into actual appropriate version. Okay. And also, if you have 5 qubits, all these 5 qubits are connected in particular way in the hardware terms. Okay, it is like a wiring and soldering between all these qubits. Imagine in this way. Okay, so how these qubits are connected together? Based upon this topology and architecture, your result may vary. Okay, the output of your quantum circuit or quantum program is always dynamic. Suppose if you are executing your result in quantum system now, okay, you will get some certain accuracy, certain error value. After some point of time, if you are running the same program in the same hardware, the dynamics of your qubit get changed. By that, your output, your accuracy, your noise also get changed. Okay, so imagine each and every qubit have dynamic nature. Okay, so sometimes it will work in very good condition, sometimes it will go for some decay, some error to noises. Okay, so it is totally dynamic. In classical, you don't have this type of problem. Okay, so frequently error will happen, destabilization will happen in cubic connectivity. So if you are choosing the wrong connectivity for executing your code, your output will get maximum impacted. Okay, so not only your coding, errors also happens more frequently in your quantum circuit. So this is the biggest drawback in quantum system. So errors will keep on occur naturally, and so many parameters that also influence these errors, right? So this is most challenging part in quantum. That is why the hardware part is not evolved rapidly. So transpilation, we can see certain definition. If you are from computer science, you're able to understand this exactly in this system. Okay. So transpilation occurs in series of passes. For each and every output of one process becomes the input for the next one. Okay. So the transpile pass define a standalone circuit transformation. The pass manager is a list of transpiler passes grouped up into logical units, and a staged pass manager is a list of pass managers, with each one representing discrete stage of transpilation pipeline. We'll see with an example. Okay, the first one is initialization, where you are preparing your circuit initial stage. It is the step one. Okay, next, if you are putting any qubits, if you are creating any qubits, then these abstract qubits circuit are mapped into physical qubits on devices. The next phase is routing. Suppose if you are using swap gates, if you are having any control node, so all these 2 qubit or multi-qubit gates will do interaction between your qubits. Okay, so it will enable interactions. So this will have a routing. So next, if you go for translation, whatever you designed your circuit, that is translated into actual quantum hardware. Okay, this translation will happen at step number 4. Next, fifth one, you need to optimize. Even though if you are translated, you need to reduce the number of gates, number of depth, number of circuits, number of width. That process is called optimization. So if you're from EC background, you can understand min-max concept. Okay. So each and every time we try to minimize a circuit by combining all other possible logic gates. Okay, logic combination. Okay. So this belongs to optimization. The last one is scheduling. Once you transpiled all your quantum circuit, then you need to wait for scheduling. So based upon the pulse sequence, you need to determine when to pick your hardware information. Okay, so this is the example for transpilation. So whatever you do in previous circuit, I will show the previous circuit. So this is your previous circuit, right? So look at the code, how it appears. So look at the basic gate, how it appears. But if you actually run for a quantum system, quantum computer, your circuit is converted in this equivalent representation. Okay, just Hadamard gate, control not gate. Look how it appears in actual quantum hardware. Okay, so these processes get done by transpilation. Okay, you no need to do transpile. The software will take care each and everything, which is most difficult part. You have to know what is happening in the background. Okay, then if you have this server, you are able to write a efficient quantum circuit each and every time if you go for real time. So that is why I'm handling this topic to give awareness. Okay. So next phase in verify phase, you test your quantum program by running them on simulated devices and exploring their performance under a realistic device noise model. If you go for simulation, you're simulating noise model also. So this is important point. So if you go for quantum simulation, what you are doing, you are adding noise model. You are doing noise model. So this noise model will mimic actual noise, actual real-time noise. Okay, then only we are able to believe simulation results. Okay, the cost of simulating quantum circuits scales exponentially with the number of qubits. That is why you need to use a small number of qubits as much as possible for learning purpose. Once you learn, if you really want to execute quantum hardware, then go for real execution. So here there is a clear note. You cannot simulate quantum circuit beyond 50 qubits. Suppose if your problem contains problem demands more than 50 qubits, you cannot do simulation. You need to go for actual quantum execution. Even though if you are using supercomputer, your supercomputer will not support more than 50 qubits. Okay, this is the physical limitation we have. Even though if you combine all supercomputer in this entire world, it won't simulate more than 50 qubits. Okay, so always test the smaller version of your circuit modify accordingly, then go for real execution. So whatever you asked, all these answers are available. There are several simulation tool available for you. So QuizKit reference primitives are there. QuizKit AR primitives are there. QuizKit AR stabilizer simulators are there. Go and explore all the simulator and you try to find difference between them. Okay. So each and every tool designed for a specific purpose. Okay. So actually explore all these tools. By the time you're able to know which tool is more suitable for your research problem. So estimator primitive, we discussed in first two slides. So estimator primitive is used to estimate the expectation value of an observable. Okay. So whatever, if you are expecting, whatever you are about to observe, that is called observable value. So this is a sample experiment of expecting value ZZ. Okay. So observable is ZZ. If you are writing this estimator code, and you will get actual value what you are expecting out of it. Okay. So the exact value is primitive is very basic. You can consider like built-in data type, which is primitive. Okay. So according to this primitive, we can build your expectation values. You can go for derived data types, right? In computer, in the same way, they gave basic tool with the help of primitive estimator. Then you can tailor for your need. Okay, this is the built-in estimator what they are giving. So this is an example for simulation noise. Suppose if you are using 127 qubit, so each and every qubit is connected in this way. Imagine you have 127 electrons. So all these electrons are connected in this way. So 0th electron connected to 1 in this way, and 1 electron is connected to 2. Okay. So 0th electron connected to 18 via 14. So likewise, each and every electron only able to communicate in this way. Only able to communicate in this way. Okay. So each and every electron have some noise level or error level. Okay. So look at there. If it is dark navy blue, it is more stabilized. Okay. If it go for this violet color, more prone to error. By looking at your color code, you are able to identify how stable it is, how error occur frequently for that particular qubit. So try to avoid this violet color as much as possible because it occurs more noise. It occurs more noise. Okay. So this type of technique belongs to error mitigation. Okay, error correction. So error mitigation you can avoid. You can do by avoiding those qubit connectivity. So error correction means if any error happen, you need to counter against it. So this is an example for a noise model. Suppose if you are from EC background or EEE background, you know how noise occurs. In the same way, in quantum also, we need to deal with lot of noises. So even though if you are not doing anything, error will accumulate over the time. Okay. So noise is inherent to a quantum system. You cannot avoid noise. But always we try to reduce the noise level. Okay. So this is an example. I will share this slide, go for your free time and refer. So once you have all this stuff, then you can able to stabilize your circuit. Okay. So there is a method called stabilizer simulation. Once you do, your circuit are get stabilized. So you can watch over here. You can watch over here. So you need to use stabilizer for your estimator. Then all your given circuit is stabilized. So finally, what you're supposed to do, you need to run your quantum system or program on real quantum system. Okay. For that, you need to follow these steps. You need to follow these steps. Okay. So the user able to construct and design a quantum circuit. The user able to design a quantum circuit. So whatever the circuit you are designing, you are using quantum programming languages. Take an example of Python using Qiskit library. So that is transferred to cloud service, where IBM Qiskit runtime will take care about all these steps. Okay, so this will forward to server, and whatever you submitted for a real-time quantum system, it will stay in the queue. Okay. So once you got your chance, your program is transferred to control electronics. Your control electronics will convert all your transpiled code into microwave pulses, microwave sequence. So all these signals went through quantum processor, and it will get executed. The computer result again sent back to control electronics in the form of electrowave pulses. Okay, your control electronics will convert these pulses into program version. Again, it will send back to your server. So once the output is cleared, it is sent back to cloud server. Then it will reach your desktop, reach your account. Okay. So once you submit your quantum program, it will stay 1 day, 2 day, according to the queue length in the server. Okay. For scientists and researchers, they have priority queue. For user like us, it will take some more time. Okay. So this is how we are able to access the real-time quantum system. So here, the system will automatically decide. So system will note what is the priority for you. Okay, it will decide. So this is an example of a real quantum system, IBM Brisbane. It is a quantum system name. Okay. So you will get backend from the system name, and if it is free, it will assign to you. If system is assigned to you, then you can run all your quantum circuit in the system. Okay. If you run, actually this circuit is submitted to this system. This system will execute, will fetch back result for you, and this is display. So each and every time you will get some session ID. The session allows the collection of jobs to be grouped and jointly scheduled by Qiskit runtime, which will facilitating iterative use of quantum computer without incurring queuing delays on each iteration. Okay. So suppose if you want to run multiple times, it will create a session. So whatever, if you want to run multiple times, it will get executed within a single job ID, session ID. Okay. So each and every time what happens, it will execute on quantum computer. Also, it will execute on classical computer. Okay. Some part the quantum computer need to execute. Some part your classical computer need to execute. Okay. So each and every time a session is typically created as a context manager using with statement. Okay. Either you can create, or the backend it will create for you, right? So each and every time you are able to create a session. So under a session, you can submit multiple jobs. The next important aspect is shots. So shots is the number of times you are executing your quantum program in actual quantum system. Okay. So normally by default, they will execute 1024 times. Though now they increase to 4000 times. Suppose if you are submitting a simple job, a small circuit, so how many times it will get executed by default? It will get executed 4000 times. Okay. So that is the meaning of shots. Okay. So why we need to execute multiple number of times? The more number of times if you are executing, more accurate you will get the result. More accurate you will get the result. So here I will take some pause. I try to explain how quantum system works. Suppose take an example of doing 2 plus 2 addition. So our aim is to do 2 plus 2. Okay. We are writing two types of code. So, So our aim is to write 2 plus 2. Okay, our aim is to write 2 plus 2. We are writing two different types of system. One is classical programming. One is quantum programming. Okay. So when you write a classical programming, you know your input, A equal to 2, B equal to 2. Okay. Here also Q bit, quantum bit, A equal to 2, B equal to 2. Okay. Next, what you are doing? You are doing a process. Okay. C equal to A plus B. Here you are writing the same way. Quantum process is equal to C equal to A plus B. But when you're writing program over here, if you're executing first time, you'll get output as 4. So here, first time you are getting output as 4. Okay. If you're running for second time in classical system using Python, C++, second time also you will get result as 4. But in quantum, second time you'll get output as 3. Third time in classical system, you are getting output as 4. Third time in quantum, you'll get output as 2. Fourth time in classical, you'll get output as 4. So in quantum, fourth time, you'll get output as 1. Very good question. Okay. So you know your input, you know your process, you can predict your output. But in quantum, you know your input, you know your process, you cannot predict your outcome. Okay, because the classical programming entirely based upon deterministic nature. Okay, the quantum programming entirely based upon probabilistic nature. This is the key point. Okay, in classical, each and every time, you know what your system will generate. But in quantum, each and every time it will generate a random output. But how to justify this? You need to run much more times. So in classical, one execution is enough. Okay. In quantum, you need to run 1024 times or 4000 times, which is the means of shots to get correct output. Okay. If you are executing for 4000 times, imagine in such a way. If you are executing the same program for 4000 times, then miracle will happen. What happens? There will be difference between occurrence of your output. So 80% of time you'll get output as 4. 10% of time you'll get output as 3. 5% of time you'll get output as 2. 5% of time you'll get output as 1. If you do statistical analysis, 4 will get 80% of time. Okay. And 3 will get 10% of time. And 2 and 1 will get 5% of time. Okay. So quantum will not only generate correct output, will generate multiple kind of output. It is a combination of both correct and wrong. But classical, always it will generate correct answer. So our life, the entire process in this universe, ultimately random in nature. Okay. So quantum behaves in such a way. So randomness is intrinsic property of quantum computing or quantum nature. That is why we are getting different kind of output. But if you want to know the correct output, you need to run for multiple times. It is like learning good thing in our life. more and more, if we are getting the wrong things, we are get punished, and we are able to direct towards the good thing. So that is how we are brought up from school to right now, right? So more and more reward for good thing, more and more punishment and penalty for wrong things. Okay, then you can do multiple level optimization. So the software will give preference for you. So if you know all this optimization level, you can use Quizzkit in better way. So I'll share with you. In your free time, go and read this. So these are the resources you can use for Quizzkit learning. Okay, all about this framework, everything you can get from YouTube also. So this is the Quizzkit platform. So I'll share this link with you. Okay, here it is, the tool. Can anybody put chat in the chat box? Yes, thank you. So go to this link. Go to this link. So if you have Gmail account, you are able to create a login in Quizzkit. Go to this link, click sign in. Click sign in. If you have Gmail account, you can use your Gmail account to create an account over here. Already created account over here. So nowadays it is asking about credit card. So if you are billing, please give your credit card details. So once you're logged in, you will land up this dashboard. You will land up this dashboard. So go down. Here you can see lot of options. Documentation, if you want to know tutorials, APIs, what you asked in previous question, you can go for documentation. So they gave the brief explanation of each and everything what we discussed so far. We will discuss, sir. Ganesha will discuss. So whatever we discussed, they gave in very detailed way. So go through this. Okay. Then you will have quick start. So whatever you are asking, everything is given over here. So go to this web page, try to explore by yourself all the API, all the advantage, disadvantage they gave. Okay, whatever the introduction about primitive they gave. Primitive is like basic fundamental. Okay, like data type in classical. I can say closest to that. You can consider like base class. Okay, so if you want to know Quizzkit add-ons, you can go here. So many APIs are available. So in future, they able to create lot of APIs. So you can find in add-ons. Okay, this is about Qiskit. See, what is the advantage of using quantum? Each and every time it is giving the correct output and wrong output. Even for doing 2 plus 2, we need to run for 4,000 times. You can ask why we need go for quantum. Okay, so quantum is not efficient for adding purpose, additional purpose. Okay, for addition, classical computer beat quantum system. But if you want to do factorization, suppose if you are giving a prime number, a very large prime number, and if you are asking your system to find its co-prime, in those scenario, quantum will take advantage. Classical will not do any great stuff. Okay, so using quantum is entirely depends upon what is your problem context. For addition, it is useless. Okay, but doing prime factorization, quantum is very, very good. It will beat any supercomputer. Okay, so it is entirely based upon your problem. Okay, quantum is not champion in all the tasks. It only champions in hard problem where so much of combinations available, so much of permutation involved. In those cases, quantum will win easily. Any process involved with random guess, any process involved with random calculation, quantum will do a lot better than classical. I hope you got the idea. Yeah, yeah. Because you can see all these tools go for Amazon bracket or Google or Microsoft. No MNC or no tool have comprehensive definition on documentation like Qiskit, IBM Qiskit. So in my point of view, IBM is leader, the foremost leader. They gave everything like open, everything like open. You can have lot of text, lot of tutorials. Okay. So no company ever launched this much of material in quantum. So that is why the Qiskit is widely used. Right? Screen is visible. I hope so. So if it is not visible, rejoin. Rejoin.
Yes, sir, it is visible, sir.
Yes, sir. So next, we are about to look about penny lane tool. So I'll give link for you. So this is the penny lane tool. So this is very good tool. This is very good tool. Where to put chat box? Accessing this chat box become little difficult. Put some message in chat box. Yes, thank you, thank you. Yes, go to this link, penny lane. So this is a tool developed by Xanadu, a software company in Canada, a quantum-based software company in Canada. Okay. So in my point of view, this stands next best to IBM Qiskit. Okay. It contains so many library packages, demo, especially in quantum machine learning. Okay. So their tool is very easy. And if you know Qiskit, you can easily learn penny lane. If you know penny lane, you can easily learn Qiskit. You need to install. If you have Jupyter Notebook, you can install, or if you are using Google Colab, you can install. You can install. Okay. So click install. They will tell all the commands what you're supposed to do. You can use VS Code also. Exactly. You can use VS Code. For each and every platform, they gave tutorial. So don't worry about that. So how to install in Linux, how to install in Windows, how to install in Mac. Okay, they gave tutorial. So don't worry about that. Okay. So this contains so many quantum hardware. Suppose if you want to use AWS, if you want to use IBM Quantum or Google SIRP or IonQ, you can browse lot of devices, actual quantum hardware, and you are able to access all these hardware through penny lane coding. Okay, you can do everything in Qiskit also, but through penny lane also you are able to do. So even though all these quantum developers, they have rivalry, but they are collaborating to each other. So you can see the good thing. So Xanadu, AWS, Google, IBM Quantum, Microsoft, IonQ, Rigetti, Unitary Fund, Quantum Inspire, all these quantum companies are collaborating each other. They are supporting their tool from different platform. So I try to explain basic about this tool. Okay. So it is a software framework using for different table quantum programming. So give me a minute. I need to power. Yes. So it is software framework for differentiable quantum programming. If you have quantum program, you able to differentiate little by little. Okay. So it is based upon Python library. Once you know Python, you able to execute penny also, and it will do just-in-time compilation. So it will not take so much of time. Okay. So it is not a programming languages. It is a framework. Okay. Suppose if you want to use TensorFlow, PyTorch, which is similar for quantum, right? Then you can train your variational quantum circuit, which is another subdivision of quantum computing. So majorly it is used for quantum machine learning. Yes. So I'll share this slide. Go and try how to install, I guess, step by step. If you are not able to do, refer the given website. They gave clear instruction. Okay. So once you install, you're able to check whether it is executed or not. For VS Code, they gave coding part. For Jupyter Notebook, everything they gave installation guide. So these are few normal exercises. So once you are familiar with penny lane, you try to solve these small exercises. We'll see what is there in their website. Okay. So 49 devices it is supporting now. Suppose if you want to teach, you can approach them. They will give syllabus. Okay. They will help you. So these are the education partners. You can see a lot of topmost university they tied up with Penny and they are using in their teaching learning process. Okay. So this is very famous university, University of Waterloo. So note down this university, University of Waterloo. So this university is doing research in quantum computing for past 30 years, 35 years. It is in Canada. Okay. Most of the Penny Lane and Xanadu software developers are from this university existing in Canada. So one of the topmost university in quantum. I'll share this link with you. And they are offering masters in quantum. Masters in quantum. So promote this among your students. See, from this website, you can see demos, not only demos. If you want to learn quantum computing, you can take part in challenges. So learning by challenges will give some pressure under the specified timeline. And they are giving so much of code books. Code book means they are giving so much of examples. So you can browse variety of modules. So each and every module code book contains definition. Suppose if you want to know basics of penny lane fundamentals, so click this. It contains 6 topics. So try to cover each and every topic and be able to get what they are meaning. So it is like a crash course. It is like a crash course. So I'll share this link with you. So go and check how easy it is. So please try to rejoin if my voice is breaking. Okay. For each and every topic, they give support like that. Okay. Then you are able to install, you're able to copy paste all this code in Google Colab. If you have Google Colab, you are able to do all this stuff. Okay, read one by one, learn at your own pace. So no hurry. Okay. So if you know Quiskit, 80% you are able to understand from Penny Lane. So that is good thing about interoperability between all these tools. So next, we're going to discuss about Universe. So Universe is a tool developed by CDAC. You need to do research, sir. We can do it in Notebook also. Yes, Notebook also. So Universe is a tool developed by CDAC. This is very good tool which is based upon Quiskit. I'll share this link with you. So go to this link. Go to this link. So this tool developed by CDAC. If you have Gmail account, you can use it. You can register. You can ask access further. Okay. Sometimes they will do immediately. Otherwise, they will take 1 day time. So already created login. I try to log in. I will show how it look like. So this is how Kiniverse look like. So Kiniverse contains this framework. So Kiniverse is unified platform, just like Qiskit, what I showed for you. So it gives the way for developers, researchers, enterprises engaging with quantum technology. So in future, they try to integrate with actual hardware. So right now they are not integrated any quantum hardware, but in future, if Indian government have any quantum facility, okay, they try to integrate that quantum facility through Kiniverse, right? So this is the architecture. So what we discussed, two tools, this Qiskit, penny lane. So all these quantum transpiler are integrated with CDAC. Okay. So what you can do, you can construct any quantum circuit through any tool and be able to optimize and be able to simulate, execute in real hardware. Either you can execute in CPU, GPU, vector or FPGA, everything is based upon simulation. But in future, if any superconducting hardware is there, able to execute. So right now they gave API integration with IBM Quantum. Suppose if you have IBM Quantum ID, you can register with Universe, then you able to execute real system. So this is a complete ecosystem. They have unified interfaces. Okay, agnostic. You can run on variety of hardware, and it contains SDK, full software development kit. Okay, where you can design your circuit, you can verify, you can compose, then you can execute, you can see visualization. If any error happens, you can see that error and you can see the equivalent code. Everything is integrated. And this universe contains so many algorithm libraries, already built-in libraries. So it will help you to develop your solution much more faster. Okay. So right now they are integrated classical and quantum workflow. They are using Param HPC. Now the time also you are able to select your Param Shakti supercomputer. Okay. And they are building tutorials. I cannot say they have a great resource. They are starting from scratch. They keep on adding all these tutorial. Each and every day it becomes better and better. Okay. So these are the 5 key points they have in their mind while developing this tool. They try to reduce your development time. They simplified hardware access. Either you can use GPU, CPU, or FPGA or quantum hardware. They try to increase debugging options and testing option before executing your circuit. Okay, and they integrated so many different kind of hardware and software packages. Okay? It means they are giving immersive portability and flexibility. And each and every day they are adding their repository. By doing 1 or 2 years, they will have matured learning curve. Okay. So this is about Kiniverse. The last tool is QSIM. The last tool is QSIM. This is developed by CDAC. They collaborated with IAC and IIT Kharagpur. So go and check this tool, QSIM. So if you have login, you can log in. Otherwise, create a login, require access for them from them. You need to mention the purpose. What is the purpose to use this tool? If you mention, they will give access code for you. Okay. So if you know Qiskit, if you know, you can work in both Kiniverse and Quasi. Ultimately easy. So all these tools entirely based upon Qiskit. So one shot, if you know the tool, you can work on any other tool, no issue. So we discussed about these tools. Now we able to execute a simple gate. Simple gate. So I try to start with block sphere. I try to start with block sphere. I'll share that slide. I'll share the slide. So this slide, your email detail, I will tell, I will show you during the last. So we'll discuss little fundamental how to, what is the term of qubit. You don't have login means you need to request them. So look for register, look for request. Okay, you can found that link. Then you need to request them. You need to request. So block sphere. Why it is not coming? Because of this chat box. Close this chat box. So block sphere is a visualization tool to view your qubit. So whatever you do with your quantum bit, you can able to visualize with the help of block sphere. Okay. So all of you know block sphere. Can I skip this? Can I directly go for execution? Or some of you know block sphere, I will revise it. Can I take block sphere? Or can I directly go for simulation? Execution. Okay, refresher. Okay, revise, no issue. So block sphere is a sphere which contains radius equal to 1, like a unit circle. Okay, it is like a unit sphere. Very good, very good. It is a unit sphere. Okay. So this sphere we are dividing into two hemisphere because we need to divide it into two hemisphere because we need to represent binary system. What is the meaning of binary system? Two-level system. Okay. To represent our binary data, we are dividing this block sphere, keep it into two levels. Very good. So what we are doing, we are taking three axes, Cartesian coordinate, x-axis, y-axis, z-axis. Okay. And what we are doing, we are taking two extreme points. So these are called polar points. Okay. So this polar point is, I'll take pointer. This polar point is extreme to the northern hemisphere. This polar point is extreme to the southern hemisphere. So what we are doing, we are mapping our binary logic over this quantum system, two-level system. So what is our binary logic? It is based upon value 0, value 1. So 0 could be off, 1 could be on. 0 could be false, 1 could be true. So we are taking two opposite constructions, right? That is called binary system. Okay, black and white. Okay, black and white, positive phase, negative phase. So whatever you have opposite polarity, opposite kind of information, you can represent with the help of binary system. Okay, present or absent. Okay, so male or female. So likewise. And these 2 points are called pure states. These two points are called pure states. And what we are doing, we are taking a random point. So look at this green dot. So this random point is your electron location or any subatomic particle location. And you are generating a vector from the origin. This vector will point to the location of your quantum particle. It could be your electron. Okay. So this blue vector is called quantum state vector. So what it means? This is the quantum state vector. So this will give information about your quantum particle. Okay. So this will give information about your quantum particle. And how will you technically say it is a mixed state? It is in between state 0 and state. So it is a mixed state. And what we are doing slicing over here. We are doing slicing over here. Okay. So this dash is called x dash y dash plane. So this dash is called x dash y dash plane. And what we are doing a projection. So look at here, we are doing projection, this yellow line from this electron location to xy plane. So this will have some intersection point. This will have some intersection point. From this point, we are doing one more projection towards origin. So we got two projections. Out of two projections, we are able to create a right angle triangle. Okay. So once we got right angle triangle, we are able to apply trigonometry. Okay. So trigonometry involved with angles, right? Trigonometry involved with angle. So here we got right angle triangle. Remaining two angles we need to know. So this is called theta. Okay. So angle difference between your z-axis to your quantum state vector is called theta. Same way, there is one more angle called psi. Okay. It is the angle between x-axis and your downside projection. So we got two angles. Okay. If we got two angles, we can convert any Cartesian coordinate into polar form. So converting x by z into theta and psi, which is more natural, more easy for us instead of x by z. Okay. So take an example of theta equal to 0. So imagine theta equal to 0 means you need to have this equation. So this equation is called quantum wave equation. So this is called psi. This is called psi. Okay. This psi is equal to cos theta by 2 multiplied with stage 0 plus e to the power I psi sin theta by 2 multiplied with 1. So if you want to define any quantum particle in superposition, you need to know this equation. Okay. So how you know your quantum particle? By knowing your two angles. Okay. So here angle tends to your reference thing. So recall previous slide. What is the definition of theta? This is angle difference between x-axis to your quantum state vector. Sorry, z-axis to quantum state vector. So imagine if theta equal to 0, it means your quantum particle is pointed over North Pole. So look at the green dot. Where green dot exists? In Northern Hemisphere. North Pole, exactly North Pole. It means apply theta equal to 0, cos 0 by 2 multiplied state 0 e to the power I psi sin 0 by 2 multiplied with state 1. So sin part becomes 0, cos part become 1. Exactly. Yes. So cos part become 1. So 1 into stage 0, we got stage 0. So this is nothing but identity gate. Okay. So wherever your quantum particle is, if you apply theta equal to 0, it will stay as it is in the same location. So nothing will happen, no changes. So second example, theta equal to pi. Okay, applying this equation, theta equal to pi, you'll get cos pi by 2, sin pi by 2. So here cos term becomes 0, sin term become 1. 1 into state 1, you will get state 1. So what it means, if you apply theta equal to pi, it will do pi rotations. So mathematically, you can see it will change into state 1. It means physically pi rotations. So physically, if you apply theta equal to pi from state 0, it will go to state 1. From state 1, again, if you are applying theta equal to pi, it will go for state 0. So this is an example for NOT gate operation. It will do bit flip. It will do bit flip. So recall theta equal to 0, North Pole, theta equal to pi, South Pole, theta equal to pi by 2, it will go for equator. It is an example for equal superposition. Yes, Hadamard gate, exactly. So this is an example for Hadamard gate. So it contains both North Pole, both South Pole components. But where it lies? Exactly in x-axis. Exactly in x-axis. Okay. So look at the second angle, psi equal to pi by 2. If you are applying psi equal to pi by 2, what happens? it will move in xy plane direction. XY plane direction in anti-clockwise. So it will move that electron from x-axis to y-axis. So this is called phase shift. Pi by 2 phase shift. Okay. So if it is moving to minus x-axis, that is called pi phase shift. So recall from previous slide. So we have block sphere. So block sphere, we have state 0, state 1 in z-axis. Okay. We have positive and negative in x-axis. Okay. We have minus I and plus I in y-axis. So with this, we can form three pairs. So state 0, state 1 in z-axis, positive and negative in x-axis, I and minus I in y-axis. So plus and minus represents real component. Your x-axis contains real components. Your y-axis contains imaginary component. Okay. So any quantum particle can be expressed in the form of complex number. That is why complex number involves with both positive component and imaginary component, real component and imaginary component. Now look at here. Where a state 0 exists in the northern pole. So north pole exists in your block sphere in upper part. So that is why the upper component become 1. So this is the matrix form of state 0. This is the matrix form of state 0. So this will note all this terminology if you are new to this. So note down, this is ket, AET ket 0. Okay. So this is upper component. So this is upper component. This is lower component or hemisphere. Hemisphere, you can see upper hemisphere, lower hemisphere. Okay. The upper hemisphere is 1 because 1 exists in north pole, northern hemisphere. Okay. So state 1 have no correlation to state 0. So that is why we kept 0. Downside we kept 0. Okay. So this is called column matrix. Column matrix. Especially one column matrix. So if you understand this, you are able to understand state 1. State 1 existing in south pole, that is why the downside, the lower part become 1, the upper part becomes 0. So these two are opposite in nature, physically opposite in nature. That is why mathematically also opposite in pattern. So if you try to understand maths through quantum, you will get more clarity. Next, look at the x-axis, positive state. Positive state contains both components, both northern hemisphere, southern hemisphere, because it is in equator. Okay. So common to both northern hemisphere, southern hemisphere. But what is the component over here? 1 over root 2. So in a right angle triangle, in equal right angle triangle, okay. So one of the component is 1 over root 2. So it is equal for both sides. Okay. Same way. So look at the negative state, which is opposite to positive state. That is why the second component having negative quantity to depicts the opposite side of the sphere. Okay. In same way, look at the y-axis. So the second component become imaginary. Look at the negative I. The second component become minus I. So likewise, you are able to visualize all these quantum state through matrix. Okay, I'll share this link. Go to this link. You can have some basics about block sphere. So if you understand block sphere, you're able to know what are the steps you can do in quantum simulation. So go to this link. Go to this link. This is a block sphere simulation tool. Okay. So these two are called pure states. These two are called pure states. So note down if you have pen and paper. These two are called pure states. So when you create any qubit, when you prepare any qubit, you need to create in only two states, either state 0 or state 1. Okay. So now it is in state 0. Click X. X means not gate. So X means not gate. So click X. Observe what happens. It will introduce pi rotation over your x-axis. So it will come down. Okay. So what happened from stage 0? From stage 0, you applied NOT gate. It goes to state 1. Okay. Now you are in state 1. Now you are in state 1. Apply X gate and tell me where it goes. Click stage 0 from here. Sorry. Click X gate from here. Now it is in state 1, right? Click X gate and tell me where it goes. All of you able to open this link? You able to do? Yes. It will go back to state 0. Correct, sir. It will go back to stage 0. So click X from stage 0. It will go back to stage 0. So I will repeat. I will repeat. So click 0. Click 0. It will point to North Pole. From North Pole, if you are clicking X, it will go to state 1. It is like NOT operation. From 0 to 1, it is moving. Okay. From 1, if you are clicking X, it will go back to stage 0. Okay. Very simple. So you are in stage 0. Apply X gate, it will go to state 1. If you are in state 1, click X gate, it will go back to state 0. So applying 2 X gate will cancel each other, go back to original state. I hope all of you able to get. Click 0. Now click Y gate. So click Y gate. Y gate you can explain. It is not gate. It is not gate. Plus pi by 2 phase shift. So note down this point. So X gate, what it will do? It will do bit flip. Y gate, it will do bit flip along with pi by 2 phase flip or phase shift. So note down this point. I am coming to that point. So each and every quantum gate operation are reversible in nature. Each and every quantum gate operation are reversible in nature. Okay. So click 0, click Y. Observe what happens. It will go to state 1. Not only state 1, if you look downside, this is phase disk, this is phase disk, and you can see pi by 2 phase difference. So this is X plus pi by 2 phase difference. So in X gate, you cannot see this phase difference, right? So differing a phase, it will entirely change your signal. Okay. So what is the difference between sine and cos? What is the difference between sine and cos? Phase difference. So that is why sine and cos are opposite in nature. If you change the phase, you can entirely change signal also in different form. So this is 1 degree of freedom. So quantum provides 1 degree of freedom, not only not operation, you can do phase alternation also. So this will have added computational advantage. So more advantage, more degree of freedom means more computation you can do, more data you can able to represent with it. So that is the idea. Okay. So click 0, click 0, click Y, it will go to state 1. Again click Y, it will go back to 0. So apply 2 Y gate will cancel each other. Apply 2 Y gate and next to next will cancel each other. Will go back to original state. So click 0, click 0, click Z gate and tell me what happens. Click 0, click Z gate and tell me what happens. Nothing. So Z gate will do like identity gate. So in 0, in stage 0, Z gate will act like identity gate. Okay. But click 1, click 1, click Z gate, observe what happens. It will do pi rotations. It will do pi rotations. So physically you cannot see any change, can see any change. But phase you can see pi rotations. So click Z from pi in the same, it will go back to 0. So what happens here? Okay. From 1, if we are applying Z, it will go to minus state 1. From minus state 1, if you are applying Z, it will go to state 1. So it will change between plus state and minus state. It will change between plus state and minus state. Exactly opposite phase about pi rotations. So only in state 0, Z gate will not work. So anywhere in your Q sphere, anywhere in your block sphere, it will apply pi rotations. So note down this point. So only in stage 0, Z gate will not do any changes. Clicking Y from getting 0, click 0. No. See, uh, uh, try to identify the difference between gates. Try to identify difference between gates. So click 0, click 0, click Z. You cannot see any change. Okay, but click 0, click Y. Some things will happen. So Y gate will operate any point in your E sphere, any point in your block sphere. But it will introduce only pi by 2. What is the point of Z? It will only introduce phase. Okay, so Y gate will do both physically also by phase. That is the little difference. So try to compare each and every gate. So try to understand X. Once you understand, try to do Y, then do comparison. Then try to understand Z. If you understand, try to compare with X, Y, Z. Okay, good. So click 0, click 0, click H gate, last gate, click H gate. What happens? As we covered in block sphere, it will create equal superposition, equal superposition. Okay, which is true random. Where random lies, it lies in your equator. It lies in your equator. Okay, I will write from stage 0. If we apply Hadamard, it will go to positive stage. Okay, from positive state, If we apply Hadamard gate, it will go back to stage 0. Okay. So do this, write this equation. Same way, from state 1, if we apply Hadamard, it will go to negative state. From negative state, if we apply Hadamard, it will go back to state 1. So these two are opposite in nature. Okay, so click one, apply Hadamard, it will go to negative. From negative, click Hadamard, it will come back to state 1. So you can able to differentiate between where you applied Hadamard gate, from which state you applied Hadamard gate. So this will able to differentiate between your locations. So that is why quantum operations are reversible. Q-sphere, you can view multiple quantum states together. Okay, block sphere, you are able to see only one qubit. So block sphere is only for one qubit. Suppose if you are viewing multiple qubit in a single sphere, sometimes it is more complex. You cannot apprehend. So block sphere is best. Okay, after some point of time, Q-sphere will not help you. Only for smaller number of qubits, Q-sphere is helpful. For larger number, you cannot comprehend. So it is like multi-dimension, right? So single dimension, single line. Okay, 2-dimension like XY graph, 3-dimension XYZ 3-coordinate system. But you cannot visualize 4-dimension by your naked eyes. Our limitation, we are able to comprehend only 3-dimension. Is it clear? Fine. So go to this composer. Go to this composer. Go to this composer. Click here. Click here. So go to view. Go to panels. Disable code editor. Go to view. Go to panels. Enable only graphical editor and Q-sphere. Only two. Go to view. Go to panels. Enable graphical and Q-sphere. So click here. Q0. Select bin button. Click Q0. Select bin button. Click Q0. Select bin button. Click C4. Select minus button. Click C3. Select minus button. Click C2. Select minus button. So keep only one quantum bit, one classical bit. So make it like this. Only one quantum bit, only one classical bit. So initially, all qubits are initialized to stage 0 by default. By default in IBM Qiskit. Okay, so that is why it is pointing to North Pole. That is why it is pointing to North Pole. Okay, so imagine this wire like electrical wire, copper wire. Okay, so stage 0 means it is off state. It is off state. So off state means there is no power supply. No power supply. Okay. So look at here. It is a phase disk. So move your mouse over here. This gray color. Okay. So this is called phase disk. Quickly you are able to view your output. Okay. So look at the parameter. Q0, phase psi equal to 0, real part equal to 0, imaginary part equal to 0. Probability of state 1 is 0%. Because it is pointing to stage 0. That is why state 1 is 0%. Look at the Q-sphere pointing to North Pole. Okay. If you understand this, then what you can do, you can drag and drop NOT gate. So this is called NOT gate. This crossfire gate. Okay. So recall, we are starting from stage 0. We implemented NOT gate. Okay. So this represents off state. So what is opposite for off? On state, state 1. So what is the meaning of on state? Power supply will be there. Power supply will be there. Okay. The electricity will flow. The electricity will flow in this wire. Okay. Now we can see difference in your phase disk. Now you got probability of 1 is 100%. Because after this NOT gate, you'll get power supply. The power supply leads to probability of 8.1 becomes 100%. I hope all of you able to do this. Okay, as we discussed in block sphere, what we are doing, we are implementing one more NOT gate. So let us focus stage 0, first NOT gate, second NOT gate. Okay. So after first NOT gate, you will get state 1. So after second NOT gate, again you will get stage 0. So 2 NOT gate implemented next to next will cancel each other. Now we got stage 0 over here. That is why again pointing to north. So click here, click this gate, press delete button. Click this gate, you can select this bin button. So anyway, you are able to delete your gates. Now what you do? Try to select this H gate. H gate implements Hadamat gate. So H gate stands for Hadamat gate. Okay. So what is the special about this gate? This gate will generate 0 sometimes. This gate also generate 1 sometimes. So randomly it will generate 0 and 1. Okay. So how frequently it will generate 0 and 1? 50-50 chance. So 50% of the time it will generate 0. 50% of the time it will generate 1. So randomly it will generate. So nobody able to predict what it will generate in next iteration. Okay. So that is why you can see both states in Q sphere simultaneously. So this is an example for superposition. This is an example for superposition. Okay. Now what you're supposed to do, you try to do measurement. You try to do measurement. So this gate is called measurement gate. This gauge, what you form. Okay. So once you do measurement, you will collapse superposition state. So Hadamard gate will point to 2 locations at the same time. But if you do measurement, you're able to get one of the possible outcome. Because superposition state will get collapsed, you will get only one possible state. So sometimes you will get 0, sometimes you will get 1. Randomly you will get output. Okay. So select this measurement gate, press delete button. Again, you're able to see superposition state. So is it clear? So if you able to do this, you able to do in universe also. You able to do in universe. See what I do? I will drag and drop Hadamat gate. I will drag and drop NOT gate. I will able to do measurement. Click here. Okay. You are able to manage your quantum bits. So make it as 1. Here make it as 1. Save. Able to reduce to 1 quantum cell. You can select different types of views. Okay. You can select different types of views. So you'll get 50-50. So within that, I will stop my lecture today. Suppose if you have any doubt, you can ask me. I'll share my social media ID. Suppose if you have any doubt, you can contact me. You can get connect with me. If you have any doubt, you can post in chat box. Thank you all. I'll share all this code today. Whatever we conducted so far, I'll share. Don't worry about materials.
Thank you so much, sir. I hope the participants have enjoyed the tour to different simulators, quantum simulators, and definitely you have enjoyed the session, because this was the one of the important session where you could basically visualize what you have learned till date, or whatever you are going to learn in the next session. So definitely one request from our side: just go through whatever sir has suggested, whatever steps sir has suggested. Just try to perform those steps, try to visualize by your own, explore those topics. Definitely that will be more help for all of you. So with this, I would like to thank all the participants, as well as our resource person, Dr. Jayakumar sir. So thank you so much, sir, for
Thank you, sir.
joining us
Thank
today.
you.
So we will be meeting tomorrow at the same time. So thank you so much, participants.